The last thing you did before closing your eyes last night may have determined whether your body spent the following 8 hours storing fat or burning it. Not what you ate for dinner 3 weeks ago, not your genetics, not your age, what you did or did not do in the hours just before sleep. And if you are over 60, the difference between those two outcomes is not minor. It is the difference between a metabolism that is quietly working for you through every hour of darkness and one that is shifted into a mode your body was never designed to maintain for long. Right now, somewhere between the third and fourth hour of your sleep, something either is or is not happening inside you. In the adipose tissue surrounding your organs, in the fat stores distributed across your body, microscopic machinery is either unlocking and beginning to move or sitting idle, waiting for a signal that never arrived. The signal is hormonal. It is ancient. It evolved long before modern eating patterns, long before artificial light, long before the habits that most people over 60 have built their evenings around without ever knowing what those habits were quietly preventing. And the remarkable thing is this: the signal is not difficult to trigger. It does not require extreme effort or deprivation. It requires understanding what your body is actually waiting for, and then simply getting out of its way. What follows is a journey through your body across the night, through the liver and the fat tissue and the brain and the hormonal architecture that governs all of it, to show you exactly what happens when the conditions are right and exactly what disrupts it. Some of what you are about to discover will explain things you have felt for years without a name. The weight that arrived after 60 and did not respond the way weight used to respond. The mornings when you wake feeling heavier than when you went to bed. The energy that seems to cost more than it used to. These are not mysteries, they are biology. And biology, unlike time, can be worked with. Stay with this. What is happening inside you tonight matters more than most people ever realize. To understand what your body is capable of during sleep, you first need to understand what it is trying to do and what it needs in order to do it. The human body did not evolve with regular access to food. For most of human history, the overnight hours were a period of enforced fasting, and the body adapted to this with extraordinary metabolic ingenuity. It developed a set of hormonal and enzymatic systems specifically designed to sustain itself through the night by drawing on its own stored energy, primarily fat. These systems did not atrophy when food became available around the clock. They are still present, still functional, still waiting to be activated every single night. But they have a requirement. They need the metabolic environment to be right before they will run.
The central gatekeeper of this process is a hormone you already know by name but may not fully understand in this context: insulin. When insulin is present in the bloodstream above a certain threshold, the body's fat-burning machinery is effectively locked. Insulin's primary job is to manage blood glucose, to signal cells to absorb the sugar circulating after a meal, and to store excess energy as fat when more arrives than the body currently needs. It does this job with precision and speed, but it also does something else, something that matters enormously for what happens during sleep. It suppresses lipolysis. Lipolysis is the process by which fat cells release their stored fatty acids into the bloodstream to be used as fuel. As long as insulin is elevated, that door stays closed. The fat stores remain exactly where they are. The body runs on whatever glucose is still circulating, and when that runs low, it does not move smoothly into fat burning. It sends hunger signals, disrupts sleep, and sometimes wakes you at 3 in the morning with a craving that seems to come from nowhere, but is actually a metabolic distress signal. For people under 40, insulin typically clears the bloodstream within 2 to 3 hours of the last meal, assuming that meal was not excessive. For people over 60, this clearance takes longer, sometimes significantly longer, because insulin sensitivity declines with age in a process that is gradual, invisible, and almost universal. This means that the same evening meal that would have left a 40-year-old metabolically clear by 10 o'clock may leave a 65-year-old with elevated insulin well past midnight. The fat-burning window, the hours during which lipolysis can run freely, is shorter. Sometimes it barely opens at all. This is not a sentence, it is a condition, and conditions respond to change. But first, you need to understand what happens when the window does open, because what your body does in those hours is genuinely extraordinary. When insulin finally falls below its suppressive threshold, a cascade begins. In the adipose tissue, those distributed stores of fat throughout your body, an enzyme called hormone-sensitive lipase receives the signal it has been waiting for and begins breaking triglycerides apart into their component fatty acids. These fatty acids are released into the bloodstream, where they travel to the muscles, the heart, the liver, and, critically, the brain. Your heart, which is almost always preferentially burning fat rather than glucose when given the choice, shifts into a higher gear of efficiency. Your skeletal muscles, even at rest, begin drawing on these circulating fatty acids for the low-level maintenance work they perform throughout the night, repairing microdamage, synthesizing proteins, renewing cellular membranes. But the most important destination for these released fatty acids, particularly in the context of aging, is the liver. In the liver, fatty acids undergo a transformation. They're converted into ketone bodies, primarily beta-hydroxybutyrate, which then re-enter the bloodstream and cross the blood-brain barrier with a directness and efficiency that glucose cannot match during sleep. The sleeping brain, it turns out, is not dormant. It is enormously active. During deep sleep, the glymphatic system, a waste clearance network unique to the brain that was only discovered in 2013, runs at full capacity, flushing cerebrospinal fluid through the spaces between neurons and removing the metabolic byproducts of a day's worth of neural activity, including the amyloid proteins associated with Alzheimer's disease. This system requires energy, and beta-hydroxybutyrate, produced in the liver from the fat your body releases during overnight lipolysis, is among the cleanest and most efficient fuels it can use.
When overnight fat burning is suppressed, when insulin remains elevated and lipolysis never fully activates, the brain's maintenance fuel supply is compromised. The glymphatic system runs at reduced capacity. The amyloid clearance that should happen every night is incomplete. Over years and decades, this incomplete clearance accumulates. This is not a speculative connection. Studies from the University of Rochester and subsequently from multiple research centers around the world have demonstrated a direct link between sleep quality, glymphatic function, and the accumulation of amyloid burden in the aging brain. What you eat before sleep and when you eat it directly affects the fuel available for this nightly neural housekeeping, and therefore, over time, the health of the brain doing the housekeeping. If you have ever woken in the morning feeling mentally foggy despite having slept what seemed like a sufficient number of hours, this is one of the most likely explanations. The hours were there, the fuel was not. Now here is what almost no one tells people over 60 about this process, and this is the part that changes everything. The timing and composition of the evening meal is the single most controllable variable in whether overnight fat burning activates. Not your genetics, not your age, not your thyroid, the meal. Specifically, how close to sleep it falls, how much refined carbohydrate it contains, and how large it is in total caloric volume. These three factors determine the insulin curve that follows, and that insulin curve determines whether the fat-burning window opens that night, and if so, for how long. A large carbohydrate-heavy meal eaten within 2 hours of bed produces an insulin response that, in a body over 60 with reduced insulin sensitivity, can persist for 5, 6, sometimes 7 hours. In an 8-hour sleep, that leaves less than 2 hours for lipolysis to run. A modest, lower carbohydrate evening meal eaten 3 to 4 hours before sleep produces a much faster insulin clearance, even in an older metabolism, and opens the fat-burning window by the second or third hour of sleep, allowing 4, 5, sometimes 6 hours of uninterrupted overnight fat oxidation. The difference in fat burned across a single night is not dramatic. We are talking about grams, not pounds. But the difference across a year of nights is not trivial. And the difference in brain fuel, in glymphatic function, in the quality of cellular repair that the body performs when running on ketone bodies rather than on depleted glucose reserves, that difference accumulates in ways that the scale does not capture, but that the body records in every cell. For anyone who wants to follow this deeper, to see exactly how the evening meal maps onto the overnight metabolic sequence, organ by organ, the full Body Hidden Signals Companion Guide is available now. The link is in the pinned comment below this video, and if you are watching on your television, the QR code on screen will take you straight there from your phone. It covers the complete overnight metabolic journey with the same detail we are moving through here, including the specific foods and timing patterns that the longest-lived populations use without knowing the science behind them. There is another variable in the overnight fat-burning equation that sits upstream of the evening meal, and it is one that most people over 60 have never connected to their nighttime metabolism: muscle. Specifically, the amount of metabolically active muscle tissue your body is carrying into the night.
Skeletal muscle is the body's primary site of insulin-mediated glucose disposal. This means that the more functional muscle tissue you have, the more efficiently your body clears insulin after a meal, and the sooner the fat-burning window opens each night. After 60, the body loses muscle mass at a rate of roughly 1 to 2% per year in the absence of deliberate resistance or load-bearing activity, a process called sarcopenia, which is one of the most underappreciated drivers of the metabolic changes that people over 60 often attribute entirely to age. It is not simply age that is making the metabolism slower. It is the quiet loss of the tissue that drives metabolic rate and insulin clearance, and that loss is, to a significant degree, reversible. This is not a minor point. The relationship between muscle mass and overnight fat burning is direct and measurable. A study published in the journal Diabetes Care found that each 10% increase in skeletal muscle mass was associated with an 11% reduction in insulin resistance, independent of body weight or fat mass. What this means practically is that building and maintaining muscle through walking, resistance exercise, carrying weight, climbing stairs, any form of load-bearing activity sustained consistently over time directly expands the fat-burning window every night. Not because exercise burns calories in the moment, though it does, but because the muscle tissue built by that exercise changes the hormonal environment of every subsequent night. There is a particular kind of physical activity that deserves special attention in this context, and it is one that most people over 60 can do without equipment or gym access. Evening walking, not vigorous exercise, but a moderate 20 to 30-minute walk in the 2 hours after the evening meal, produces a metabolic effect that is disproportionate to its apparent simplicity. During this walk, the muscles of the legs and core act as a glucose sink, drawing blood sugar out of circulation and into muscle glycogen stores with an efficiency that is comparable to a small dose of insulin. The result is a faster, cleaner post-meal glucose clearance, a lower and shorter insulin response, and an earlier opening of the overnight fat-burning window. Multiple studies in populations over 60 have found that post-meal walking reduces the 2-hour post-meal glucose spike by between 20 and 30% compared to sitting. In an older metabolism where insulin clearance is already slowed, that reduction is the difference between the fat-burning window opening at midnight or at 3 in the morning. But there is something else happening during that evening walk that operates on a different timescale and a different biological layer.
something that connects directly to the quality of sleep that follows, and therefore to everything that happens metabolically inside that sleep. As the light fades in the evening and the body moves into the preparatory phase of sleep, a transformation is underway in the pineal gland, a small pine cone-shaped structure seated deep in the center of the brain. This gland is converting serotonin into melatonin, the hormone that orchestrates the transition into sleep and, critically, the architecture of the sleep stages that follow. Melatonin does not simply make you drowsy. It coordinates a hormonal sequence that includes the release of growth hormone, one of the most powerful fat-burning and tissue repair signals the body produces, and the suppression of cortisol, whose elevation during the night would otherwise block lipolysis as effectively as insulin does.
Growth hormone is released in pulses during the first few hours of deep sleep, primarily during the slow wave stages that dominate the early part of the night. Its effects on overnight fat metabolism are profound. It directly stimulates lipolysis in adipose tissue, amplifying the fat-releasing signal that hormone-sensitive lipase is already responding to. It simultaneously directs the released fatty acids toward muscle repair and protein synthesis rather than re-storage. And it exerts a powerful counter-regulatory effect on insulin, keeping insulin low through the middle portion of the night, even as the body draws on its own stores for fuel. After 60, growth hormone secretion declines significantly. By some estimates, total overnight growth hormone output falls by 50 to 70% between the ages of 25 and 65. This decline is real, and it does reduce the overnight fat-burning stimulus. But here is what the research also shows. The decline is not uniform, and it is heavily influenced by the quality of slow-wave sleep, which is itself heavily influenced by the behaviors of the evening. Deep, consolidated slow-wave sleep amplifies the growth hormone pulses that do occur, even in an older pituitary. Fragmented, shallow sleep, the kind produced by late eating, alcohol, elevated evening cortisol, or screen light that suppresses melatonin, blunts those pulses further. The 65-year-old who sleeps deeply and cleanly will produce measurably more growth hormone than the 65-year-old with the same biology who sleeps poorly, and the overnight fat metabolism that follows will be measurably different. This is the hidden connection that ties the evening habits together into a single coherent system. The walk after dinner that clears blood glucose is also moderately fatiguing the muscles in a way that deepens slow-wave sleep. The early, modest evening meal that opens the fat-burning window also allows the digestive system to quiet before sleep, reducing the internal activity that fragments deep sleep architecture. The absence of alcohol, which many people over 60 use as a sleep aid without realizing that it destroys slow-wave sleep architecture in the second half of the night, producing the 3 in the morning wake that feels unrelated to the glass of wine 4 hours earlier, protects the very sleep stages in which growth hormone flows and fat burns most freely. Alcohol deserves a moment of particular attention here because its relationship to overnight fat metabolism is one of the most misunderstood pieces of nutritional biology in common circulation. Alcohol is not simply a source of calories. It is, in metabolic terms, a toxin that the liver prioritizes above all other substrates. When alcohol is present, the liver stops processing fatty acids for conversion to ketones and redirects all available enzymatic resources to metabolizing ethanol. Overnight fat burning does not simply slow when the alcohol is in the system. It stops completely for as long as the liver is managing the alcohol, which, for more than one standard drink consumed in the evening, is often 3 to 5 hours. The fat-burning window, even if the insulin conditions were otherwise perfect, does not open while the liver is occupied with ethanol clearance. And in a body over 60, where liver enzyme activity is already somewhat reduced compared to younger years, that clearance takes longer still. This is not a moral judgment about alcohol. It is a metabolic fact about a specific mechanism.
What you do with that fact is entirely your own decision.
There is one more element of the overnight fat-burning system that deserves its own exploration because it operates at a level of biology so fundamental that it shapes the effectiveness of every other habit we have discussed. It is the circadian timing of metabolism itself, the way your body's internal clocks regulate not just when you feel awake or asleep, but when every metabolic enzyme reaches its peak activity, when fat-storing versus fat-burning genes are expressed, and when the cellular machinery of lipolysis is most primed to respond. The body does not metabolize food the same way at 7 in the evening as it does at 11. Research from the field of chrononutrition, the study of how meal timing interacts with circadian biology, has consistently shown that the same meal consumed earlier in the evening produces a lower and faster insulin response, a smaller fat storage stimulus, and a more efficient overnight metabolic recovery than the same meal consumed late at night. The reason is rooted in the circadian expression of insulin sensitivity across the day. Cells are most sensitive to insulin, most efficient at clearing glucose in the morning and early afternoon, and least sensitive in the late evening and night. Eating a large meal when cellular insulin sensitivity is at its daily low requires the pancreas to produce more insulin to achieve the same glucose clearance, producing a larger and longer-lasting insulin elevation that extends well into the sleep period. For people over 60, whose baseline insulin sensitivity is already reduced, the evening decline of cellular responsiveness is steeper and more consequential. A meal that a 40-year-old can metabolize comfortably at 9 in the evening may produce an insulin response in a 65-year-old that persists until 2 or 3 in the morning. Moving the evening meal earlier, even by 60 to 90 minutes, is not a trivial adjustment. For the overnight metabolic window, it can mean the difference between 2 hours of fat burning and 5. The Okinawan principle of hara hachibu, eating to 80% fullness, is relevant here not just as a caloric moderation strategy, but as an insulin management tool. A smaller meal, consumed earlier, in a body that has been moderately active in the hours before sleep, produces the shallowest possible insulin curve. It is not coincidence that the populations with the longest healthy lifespans share this pattern across different cultures, different cuisines, and different geographies. The evening meal across the blue zones tends to be the smallest meal of the day, eaten well before dark and followed by light activity. The biology of why this works is now clear. The people practicing it arrived at this pattern through thousands of lived experience without a single metabolic study to guide them. Step back now and look at what the overnight fat-burning system actually requires. Not a supplement, not a drug, not a technology. An eating window that ends early enough for insulin to clear before deep sleep begins. A modest evening meal with a lower refined carbohydrate load. A post-dinner walk that accelerates glucose clearance and deepens the slow-wave sleep that will follow. The absence of alcohol in the hours before bed, and a consistency of schedule that allows the circadian clocks in the liver and adipose tissue to synchronize their enzymatic rhythms with the timing of sleep. These are not exotic interventions. They are, in many cases, the habits of every generation before the era of electric light and constant food availability. Habits that the human body spent hundreds of thousands of years building its metabolic architecture around, and habits that the last several decades of modern convenience have quietly dismantled. The body did not change, the context did. And the body, without the context it evolved for, is running its overnight programs on a stage that no longer matches the script.
You already know some of what this feels like. The morning weight that fluctuates in ways that seem disconnected from what you ate. The energy quality in the morning, whether it arrives cleanly or costs something to generate. The mental clarity or absence of it in the first hour after waking. These are not random. They are the morning receipts of the overnight metabolic accounting that happened while you slept, readable if you know what you are looking for. After 60, the body asks for more precision, not more punishment, more precision. It has less margin for the habits that a younger metabolism could absorb without consequence, not because it is broken, but because it is communicating more clearly. The signals it sends, the weight that accumulates differently, the energy that requires more management, the sleep that feels lighter than it once did, are not complaints. They're a sophisticated biological system telling you exactly what it needs in order to do what it was designed to do every night, automatically, in the dark, while you rest. What we followed tonight is one corridor of a much larger architecture, a body that runs its most important work while you are not watching, and that needs very specific conditions to run it well. The full Body Hidden Signals Guide maps that architecture in the same depth we moved through here. The link is in the pinned comment below. And for those of you watching on the television, the QR code on screen will take you there the moment you point your phone at it. The overnight systems, the morning signals, the daily habits that either open the door or keep it closed. Everything your body has been doing in the dark, finally in full light.